So once again, good morning, folks. Good morning, good afternoon, good evening, yet again for one more time this year. So we are into our fifth installment of the Mysteries of the Universe Institute lecture series at the Indian Institute of Technology, Roorkee, India, and it's truly a privilege and such a great pleasure to have Professor Abhay Ashtekar with us today. Those of us for whom theoretical physics is their business, I'm sure Professor Ashtekar doesn't need any introduction. I'm sure most of us have. In fact, I'm reminded of there was an event which we had a workshop which we had which I organized 13 years ago. It was very humbly called IWT-HEP. It was very simple, International Workshop on Theoretical High Energy Physics. And back then we had Martin Bourgeois, Professor Ashtekar's collaborator, who actually introduced the community, or introduced the attendees of that workshop to loop quantum gravity, which is Professor Ashtekar's baby, I would say. And so I think we have even independently heard of the famous Ashtekar variables, and therefore also loop quantum gravity, quantum general relativity, quantum holonomy. So that is in terms of course, a very, very small, tiny glimpse into the incredible amount of work which Professor Ashtekar has is carrying out. But for a more formal introduction, I would say the following, that Professor Ashtekar is the director of the Institute for Gravitation and Cosmos. And he's also the Ivan Fuchs Professor of Physics, and he's the holder of the Eberly Chair in Physics at Penn State. Before joining Penn State, he was the Erastus Franklin Holden Professor of Physics at Syracuse, and he was also the Professor Chair de Gravitation at Paris 6. He was awarded Dr. Rerum Naturalium honoris causa by the Friedrich Schiller University at Jena in Germany in 2005, and by the Université de Marseille II Part 2 in France in 2010. He is a past president of the International Society for General Relativity and Gravitation. He was elected to the US National Academy of Sciences and has won the Senior Research Prize by the Alexander von Humboldt Foundation and the Einstein Prize by the American Physical Society. He's a fellow of the American Association for Advancement of Science and the American Physical Society, and is one of the only 51 honorary fellows of the Indian Academy of Sciences drawn from the entire international community. He won the Senior Forschung Prize of the Alexander von Humboldt Foundation. He has held the Kramer's Visiting Chair in Theoretical Physics at the University of Utrecht, Netherlands, and is the Sir C.V. Raman Chair holder of the Indian Academy of Science. He also chairs the International Advisory Committee of the Indigo Consortium in connection with the LIGO India initiative. So with this brief introduction, I humbly request Professor Ashtekar to kindly deliver his lecture. Professor Ashtekar, please.
Okay, so let me start sharing screen. Okay, can you see my screen?
Yes, absolutely, yes.
So the title of this talk is, as you see, Black Holes, Big Bang, and Gravitational Waves. And these are really kind of topics which are brought to forefront because they illustrate how paradigm shifts occur in fundamental science. And that really is what I would like to tell you. I mean, we kind of think that science is very objective and things happen in a very logical way, but there are many twists and turns, and how actually
Professor, I think you muted yourself.
Professor Ashtekar, you got muted. Yeah. Sorry, something happened.
Yeah. Okay, so now can you hear me?
Yeah, absolutely.
Yeah, good. So the goal of this talk is rather general discussion on the theme of paradigm shifts in basic sciences and illustrated by examples drawn from my expertise. And they bring out the following points. First, that what we now consider as common knowledge was not at all so of just a few decades ago. And in fact, much of the scientific community at the time was probably thinking in almost opposite direction. So one needs this courage to really pursue directions which may not be sort of the mainstream, may not be the common thinking, to bring about these paradigm shifts. Second, precisely because they are startling at first, the dramatic paradigm shift takes decades to get settled and become the new common pool of knowledge. And therefore, one also needs this patience to really believe in something and really wait for a while. And the third is really factors driving or slowing down the progress are quite varied. It's not a simple matter of logical steps as it is meant to appear in retrospect. So one needs this maturity to understand how really the paradigm shifts occur and how they are recognized. So the first example is really general relativity itself. And so I realize that many of you do not know about general relativity. So I'm just going to tell you about these various aspects of general relativity, and also tell you about how these paradigm shifts came about. So the main point about general relativity is the following, that most of the familiar ideas from Newtonian paradigm, space and time in that Newtonian paradigm, are really an inert backdrop or arena or a stage on which things happen. Space-time is just sitting there, and various actors are like stars and various fields like electromagnetic field, gravitational field, and so on and so forth. And that they are subject to dynamics, but in fact space and time itself is inert. And gravity is a force between two massive bodies and is universal. Given any two bodies, they have a mass, and therefore there is a force, attractive force between these masses. And this paradigm reigned over 200 years, but was shattered by Einstein's general relativity. And the main shift is the following, that space and time now fuse into a four-dimensional continuum. Its geometry, the geometry of this continuum, is a physical and dynamical entity, which is very different from what happened here, where space and time are inert in Newtonian physics. So now geometry becomes a physical entity, like tables and chairs and planets and trees outside. And so they really are physical entities. They are not static, they evolve in time. Just like matter, they are physical entities, and they can be acted upon, and the space-time then really reacts back. And this is a radical shift in the description of reality. Furthermore, this shift is absolutely essential when gravity is strong, as we will see, like when all the main themes of today's, which is really gravitational waves, of course, the Big Bang, and the black holes. So there is even a greater universality to gravitation now, because it is absorbed into the geometry of space and time itself. So as I said just now, that it is absorbed. So what happens in general relativity is really that gravity fuses with the space-time geometry. So on the one hand, we had gravity, on the other hand, we had space-time geometry. Now the two are fused together. Space-time is no longer an inert background or a stage, but rather gravitational force is encoded in the very geometry of space-time. And this is possible because gravity is omnipresent. You see, space-time geometry is everywhere and is omnipresent. And now gravity is also omnipresent. It cannot be switched off. And therefore, with gravity, you could fuse it in the very geometry of space and time. Whereas, for example, with electromagnetic forces, they act one way on positive charges, the opposite way on negative charges. So you cannot really incorporate it into the geometry of space-time itself. And it is non-discriminating in the sense that it acts the same way on all physical objects. And that is why it could be absorbed into something that is really truly universal, namely the underlying space-time geometry itself. So in general relativity, gravity tells, matter tells space-time how to curve, and these are Einstein's equations, and space-time tells matter how to move. So here is a depiction. Here is a heavy body such as sun down here somewhere, and that has bent this continuum of space-time. And here is a small body like Earth, and the Earth is actually trying to go around. The Earth is actually trying to move up here, but it really is trying to go straight. But what happens is that because space-time itself is curved, the orbit of the Earth, when looked at from Newtonian perspective, looks as though it is really a bent object. Now, the discovery of general relativity occurred, 105 years ago in 1915, and just a couple of days after Einstein sent his paper to the journal, to the Prussian Academy of Sciences, he wrote to Sommerfeld, who was a leading theoretical physicist in Germany at that time, in Munich, saying that during the last month, I experienced one of the most exacting and most exciting times of my life. True enough, also one of the most successful. And then he goes on to explain how, although these ideas are very, very radical, that space and time are bent and they are curved and so on and so forth, but this in fact does account for an old mystery, which had to do the orbit of Mercury, which had remained as mystery in Newtonian physics. So this happened in 1915, but it took 4 more years until 1919 for the scientific world and for the world to appreciate this evolution. And what was involved was really events which are really not scientific in origin at all. So it took 4 years for general relativity to be accepted as a revolutionary paradigm. And this happened because Arthur Eddington actually led an expedition to verify the bending of light, and that was predicted by general relativity. Its value is twice as big as that in Newtonian gravity, and Eddington's measurement showed that general relativity was correct. And then instantaneously, Einstein became a household name. And this was really something because of non-scientific reasons. I mean, there was a scientific reason, namely Eddington actually did do this observation, and he found that in fact the light is bent as it comes across from the sun. And here is a very beautiful example that gravitational field bends space-time, and therefore you actually have gravitational lenses. But the main point up here was that the reason why Einstein's name became so household was because the First World War had just ended. And here was a theoretical discovery made by German scientists, and that was really verified by a British leading astronomer. And science really transcends these stupid human activities like war and killings and so on. And the world was thirsty for something noble, something that transcends this follies of humanity. And that is really why Einstein became a world figure instantaneously. And here is a New York Times headlines that lights us all askew in the sky. Einstein's theory triumphs, stars not where they seem to be because of the bending of light, or calculated to be, but nobody need to worry. And then it goes on like that. So it's really a non-scientific event, the ending of the First World War, and the fact that these two countries were at war, and the science really transcended those things, which are this enmity, this war, and so on, is really what led to Einstein and general relativity to become household names. Now, general relativity is really very deep. This whole idea that something that was called force can be absorbed into the geometry of space-time is extremely non-trivial. And as Hermann Weyl says, and this is what we experience, those of us who are practitioners of general relativity experience this all the time, namely, it is as if a wall which separated us from the truth has collapsed. Wider expanses and greater depths of knowledge are now exposed to the searching eye of knowledge, and regions of which we had not even a presentiment. And here is our own Subramaniam Chandrasekhar, or Chandra as he was called by his colleagues and students. He compares the richness of general relativity to the richness of the best sculptures. And here is a Michelangelo's great sculpture up here, La Pieta. And when Henry Moore was a great sculptor of 20th century, his sculpture is in University of Chicago campus on atomic energy. He says that when he visited University of Chicago some years ago, Chandra had an occasion to ask him how one should see the sculptures, from afar or from nearby. And Moore's response was that the greatest sculptures can be viewed, indeed should be viewed, from all distances, since new aspects of beauty will be revealed in every scale. Now, Roorkee is an institute of technology, and many of you are involved, for example, in architecture, maybe, and you know this firsthand, that the greatest pieces reveal beauty at different scales, and that is true in sculpture. And Einstein says that is exactly what is true about general relativity. In the same way, general relativity general theory of relativity reveals the strangeness and proportion at any level in which one may explore its consequences. So this is all very beautiful. This really was a true revolution. It changed our notion of space and time. It changed our notion of gravity. It changed our notion of how universe functions, because everything happens in space and time. And yet one might still ask, but again, because of people in Technology Institute saying that, okay, this was a great revolution, but does it really matter in practical terms? It's all theoretical, it's all very beautiful, but does it really affect me? And the answer is yes, it does affect all of us. And we see this just, I don't know if you see me, but just in terms of your cell phone that you use all the time. The cell phone tells you your location using the GPS system, the globally positioning satellite system. And these global positioning satellites have to coordinate their clocks in the satellites with the coordinates, with those on Earth. There's a curvature on Earth, which is kind of stronger than curvature that is experienced by the satellite. And as a result, these clocks tick at a different rate. And that is something that really has to be figured in. And in fact, the GPS system of localization errors would grow to 23 meters. And therefore, airplanes would not be able to would not be able to land on the runways if, in fact, we were to ignore general relativity effects. Within 2 minutes, GPS system would prevent the pilots from landing planes on a runway. So the fundamental laws of nature always matters. You never know when they're going to matter, where they're going to matter, but they do matter. What may seem like fantasy today is often essential for tomorrow's technology, and if it is grounded in solid fundamental science. So this is general relativity. I already told you that this revolution occurred. This revolution was totally unexpected, but nonetheless, it took quite some time for it to be really accepted in the wide world. So now let me talk about black holes. This is the first topic I chose to talk first application of general relativity I chose, because this is the topic for which this year's Nobel Prize in Physics was just awarded. And what are black holes? It's really, in a sense, end of space-time. They're regions of space-time from which even light cannot escape. And now, of course, black holes are widely regarded as engines that drive the most energetic phenomena in astrophysics. We're going to see some examples of it, but interestingly, it was not always so. Today, everybody thinks, oh, of course, we know there are black holes, but it took a long time for the notion of black holes to be accepted. Here is a picture of kind of what is happening that is really that there is a black hole in the center up here, and there is a star which is around, and the star is emitting matter which is being gobbled up by the black hole. And in that process, in that acceleration, it sends out X-rays, and these X-rays can be seen. And the picture up here is basically telling you the merger of black holes that was seen by LIGO Virgo. And India is going to soon join this collaboration, so it is very interesting. So this is the first batch, so to say, of black hole mergers that we're seeing. So today it's all obvious, but it took a very long time, and this is what I would like to explain. And also today, the Nobel Prize announcement of last month, 6th of October, said that the prize was given 1/2 to Roger Penrose for the discovery that black hole is a robust prediction of general relativity. And that's what I'll explain. And the other half jointly to these observers, astronomers, who saw a compact object in the center of a galaxy. And I'll tell you about that in a minute. So it's easier to start from here, the compact object that was actually seen. And this compact object is in the center of our own galaxy. So here is a picture of Milky Way. This distance scale is about 1 light year. And the black hole I'm talking about is here, where the arrows are pointing, very, very little thing that you can see up there. So this black hole in the center of the Milky Way, it has about 4.3 times the mass of the sun. It is called Sagittarius A star, or just SGR A star. That's the name for that particular black hole. It's a large black hole, huge amount of mass. And what one sees is the following. So black hole is, of course, black. Light doesn't escape from it. So we cannot see the black hole. So how do you know it is there? What we do see is really various stars and objects in that region of space-time. And these various stars and objects in that region of space-time, people have been very astute. Even you cannot really see them in visible light because there is too much dust there, but one can see them in infrared. So these Nobel Prize winners, Genzel and Ghez, what they did was to really observe the trajectories of the star. And the one that they observed most clearly is called S2. It was just the second star that was discovered here in the center of the galaxy, orbiting the black hole. And they see the orbit of the star. So this is the thing that they actually see. And then one can see, so you can see that, this has happened. It takes many years for the star to actually go around. So the observations have been taking place from 1992 to 2018. So it's really 26 years of observations. And then what one sees is the following, that the star is orbiting as though there was some heavy object at the center, and that is the black hole. So the black hole existence is, so to say, is realized by observing the orbits of stars around them. So then the statement is really the following. Is this something that is totally surprising, or is this something that was anticipated? Now, amazingly, this prediction that black holes, maybe even though they are invisible to the eye directly, they could be observed indirectly, was something that was made by John Mitchell in the Philosophical Transactions of the Royal Society already in 1784. And he said, if there should exist in nature any such bodies, we could have no information from sight, because the direct light will not come to us. But yet, if any other luminous body should happen to revolve around them, we might still, perhaps, from the motions of these revolving bodies, infer the existence of the central ones to some degree of probability. And as we saw, this is exactly what Genzel and Ghez did. They deduced the existence of this object, the compact object, by looking at this orbit of the star, which is going around it. So, so one might say, well, that this is all fine, but is this really just one second. Yeah, unfortunately, sort of, I'm missing a slide here. I'm sorry about that. But what happens is the following: that in fact, we need. It's not enough to just take Newtonian gravity. It turns out that Newtonian gravity by itself is not sufficient to talk about black holes in a self-consistent manner. The reason is because even though you can have objects from which in Newton's theory would predict that light cannot escape from this object that is emitted by this object, because the escape velocity for this body might be greater than the speed of light. That is what Newtonian gravity would say, that then you could not see the object. And that is what Mitchell is here talking about. But this is not really completely right, because even if we cannot see the object, the light emitted by the object, in Newtonian gravity, you could have light which is really shown on this object. For example, for the moon. The moon doesn't emit any light, but on the other hand, the sunlight is actually incident on the moon and is reflected by moon. In Newtonian gravity, if you have such a compact object, candidate black hole, still the light from another object like the sun would fall on it. As it falls in Newtonian gravity, it would keep accelerating, and it can have speed bigger than the speed of light, because there's nothing in Newtonian gravity that says that the speed of light is the ultimate limit. So it will actually, when it actually falls on the moon, the velocity will be greater than the velocity of light as in the rest frame of that particular object, such as the moon up here, and then it will be reflected. So because the incoming velocity was bigger than the velocity of light, by conservation of momentum, light could be reflected, and then we would be able to see it. So in fact, one needs general relativity to talk about space-time. And here is a diagram that is due to Roger Penrose that was included in Nobel Prize announcement. What happens is the following: time is running up and space coordinates are like that. And what happens up here is really that you are got a star up here, matter, and in time its radius shrinks and it collapses and it forms a black hole. And then what happens is that in the central region, there is a region of space-time in which light cones, the direction in which light can propagate is its future direction. These light cones are actually bent so much that light really is trapped here. Light cannot go out at all. So there is an absolute trapping of light in some region, and that cannot really be something that is not observer dependent, that does not depend with respect to whom one is measuring the speed of light, because speed of light is universal constant in both special and general relativity, and therefore you have got these regions of space and time in which light cannot escape, and these are black holes. So this was the prediction of general relativity, and that is the slide that was missing that I just explained. But then one would think that, well, okay, then in general relativity, we would have the notion of black holes without any problem. But even here, the history is very curious. The simplest black hole solution was discovered by Schwarzschild also during the First World War I. But a clear notion that it's a black hole, the interpretation of this solution as a black hole, had to await several decades, both because leading researchers did not understand the interplay between physics and geometry very well, and because the geometry, the understanding of geometry was not really so deep. So initially there was a great confusion about what one is called the surface of this black hole, this event horizon, at which the solution is deep and was supposed to break down. And this was really finally cleared up, saying that there is nothing wrong about here, it's just the light is trapped. And in fact, there is a singularity in the center of the black hole, but not here. Here, everything is perfectly fine, and there is a finite region in which light is trapped. So that was what was shown. And furthermore, there were discoveries, particularly by Chandra from 1931 to 1935, and this was about the fate of heavy stars. And the first calculation that Chandra did was during his boat trip at the early age of 20, while he was going to Cambridge for his PhD. And he showed that if you have heavy stars, then these heavy stars, after they have burnt the nuclear fuel, they would collapse. And that collapse would actually cause the star to turn into black hole, as I had seen in the space-time diagram before. So this was already done really a long time ago. And then in 1939, Oppenheimer and Schneider actually studied this problem in great detail in general relativity. They considered a ball of dust which was collapsing under its own gravitational field. And they found that this ball of dust actually does collapse to a black hole in general relativity using exact general relativity. What Chandra had shown was the following, that when a star actually burns its nuclear fuel, then it cannot be in equilibrium. Our sun, for example, is in equilibrium because it is emitting light as it burns nuclear fuel. And that light pressure of the outgoing light pressure is balanced by the gravitational attraction. But once nuclear fuel ends, there is no light pressure. There is no emission of light, which will actually exert a pressure. And now the star will start collapsing. But in quantum mechanics says that if you have got two particles which are spin 1/2 called fermions, then they cannot be in the same state. Therefore, quantum mechanics exert a certain force on these particles, but that force is repulsive. But that force is not sufficient to balance the gravitational attraction if the star is sufficiently massive, and then the star will collapse and form a black hole. So whereas Oppenheimer and Schneider actually did a detailed calculation using Einstein's equation. In the Indian literature, there is some recently sort of a claim that Professor Dutt from Calcutta had actually, he did have this paper in Zeitschrift für Physics that actually predated Oppenheimer-Schneider. I looked at the paper in great detail, and this is not quite true. He did find a solution, but he did not understand the physical meaning of that solution, whereas Oppenheimer and Schneider really found this solution because they wanted to get to the black hole. And they talk about light being trapped, just as we have seen in this picture, that this is what happens, is what Oppenheimer and Schreider showed. Okay, now one might say, well, okay, so this is all done by Oppenheimer, Schneider, and by Chandra, but still there is a strong reluctance in accepting the idea that that stars more massive than the Chandrasekhar limit have no equilibrium configuration once they exhaust their nuclear fuel, as Chandra showed. There is a great reluctance to this. And it really is some aesthetic judgment, because astronomers really prefer a serene and calm universe, not a violent one. And there was also a quirk of history. In 1939, when this paper appeared, Oppenheimer Schneider, was the same day that Bohr and Wheeler wrote their paper on nuclear fission occurred. And this was now Second World War, and there was a great concern that Nazis would have the nuclear bomb, and therefore the whole attention of the world was on these kinds of things about the worries about Nazis. Hitler invaded the Poland exactly on the same day as this paper appeared, and so the world was distracted, and this paper was not taken very seriously either. And there was a really reluctance in accepting the existence of a black hole. People really would like to believe that the universe on a very large scale is a very serene place. Violent events don't happen. Violent events such as those leading to the black hole formation just don't happen. For example, Eddington, the same Eddington that we saw before, the same picture again. Eddington, in fact, came forcefully against Chandra's ideas and saying that various accidents may intervene to save the star. And Eddington was at that time the president of the Royal Society of Astronomical Society, and therefore, his words carried a lot of weight. And Eddington sort of went on to say that various accidents may intervene to save the star, but I want more protection than that. I think there should be a law of nature to prevent stars from behaving in such an absurd way. I mean, this argument would just, if some physics student gave it in their comprehensive exam, they would fail the comprehensive exam. And yet, the leading astronomers, and so somebody who understood general relativity, was making such an argument. And Einstein himself, in 1939, the same year, just a few months before the Oppenheimer-Schneider paper came, wrote a paper talking about impossibility of gravitational wave through gravitational collapse. And Oppenheimer-Schneider paper came just a few months later. And Einstein's calculations were not wrong, but he made an assumption that this collapse would occur very adiabatically, very slowly, whereas it happens very rapidly. So there was this great reluctance. And what the Nobel Prize was given was because Roger Penrose's 1965 paper showed, without any symmetry assumptions, see, this paper of Eddington's, this paper of Oppenheimer and Schneider assumed spherically symmetric gravitational collapse. And so people thought that, well, okay, maybe if a star is really spherically symmetric, it might form a black hole, but most stars are not exactly spherically symmetric, therefore they would not form a black hole. But Penrose's paper showed, without the assumption of spherical symmetry, that if you accept general relativity and physically available matter, so technically satisfying energy conditions, then gravitational collapse would inevitably lead to a space-time singularity. And therefore, there is, again, come back to the announcement of the Nobel Prize given to Roger Penrose for the discovery that black hole is a robust prediction of general relativity. Now black holes are invoked as engines driving the most energetic explosions in the universe very routinely. Here is a black hole, which is basically the material is falling into the black hole, and therefore you got X-ray emission. Here is a gamma ray burst. When the two neutron stars actually merge and form a black hole, then there's a big gamma ray burst that occurs, or a single neutron star collapsing, forming a black hole. Then there's a burst that occurs. And in this case, in a few blinding seconds, more energy is emitted than what 1,000 suns do in their lifetime. And here is a picture of two galaxies merging. Each of these galaxies has a black hole in the center, and they will also merge. But this is not really something that is now accepted today, because black holes is commonplace to explain astrophysical phenomena. But as we saw, it was a winding road to arrive here. So now let me talk about birth of modern cosmology, which is the Big Bang and so on, which really is also a big paradigm shift. So cosmology results because one applies general relativity to the universe as a whole. So this is a big jump. Einstein discovered general relativity, for example, the first evidence came from the solar system, but then he applied general relativity to the universe as a whole. And when you look at the symmetries of the universe as a whole, homogeneity, there is no spatial place in the universe, and isotropy, there is no spatial direction in the universe. That together with Einstein's equation immediately tells you that the geometry must be dynamical and related to matter via Einstein's equation. And the standard picture then is that the universe began with a primordial explosion depicted up here in about 13.8 billion years ago. And this is a big paradigm shift that has occurred. But again, this paradigm shift has a curious history, and it was not accepted by scientists for a very long time. In fact, immediately after general relativity discovery, 2 years later, Einstein, and then simultaneously or a little later, de Sitter discovered solutions from Einstein's equation in which the universe is eternal. So here is a picture. This is a picture of the de Sitter universe. So here there is no beginning, there is no end. Time is running this direction as one sees up here, and therefore the universe exists forever and goes on existing forever. In Einstein's picture, the universe was static, so in space and time, it looked really like a cylinder, so it's called Einstein cylinder. And de Sitter picture, it is actually evolving in this particular way, but still there is no beginning, no end, there is no Big Bang at all. And then it is really in the 1920s that Friedman and Lemaitre, Friedman was a Russian astronomer and mathematician, and Lemaitre was a Belgian actually priest who was a mathematician and astrophysicist at the same time, who understood general relativity very well. They discovered the solutions which we use today, in which the universe begins with the Big Bang. Again, time is running this way. These are spatial coordinates. So the universe is expanding as it goes in time. But if you go back in time, then a stage comes in which space-time itself crumbles, and there is the space-time continuum tears, and classical physics stops, and that is a pictorial representation of the Big Bang. So, but nonetheless, the Big Bang was not accepted immediately. There are many twists and turns. In 1930, again, the same Eddington that we talked about before was the president of the Royal Society and in the Royal Astronomical Society. And in the meeting of the Royal Astronomical Society, he was only looking at these two solutions, and he was saying that, well, Einstein universe is static, so should we put a little bit of motion in Einstein's universe, so make it dynamic? But Eddington's, the de Sitter universe has no matter in it at all, only geometry, and so therefore he called it perpetual mobile. And so he said, shall we put a little motion into Einstein's world of inert matter, or a little matter into de Sitter mobile? But then this completely changed, namely when Hubble discovered that the universe is expanding, and therefore the universe is not eternal. And then the whole idea that the universe, the picture was something like this, began to get some attention. And in this case, Lemaitre really played a similar role. In fact, the Hubble law is now renamed just a few years ago, 2017, I think, now is named Hubble-Lemaitre law. And there is, as you can see from this picture, Lemaitre was actually a Jesuit, and he, however, kept science and philosophy, science and religion and philosophy completely apart. And in particular, when, in fact, in 1951, when George Gamow wrote to Pope Pius telling him about the Big Bang, and Pope Pius immediately said, religion and science are coming together. In fact, Lemaitre took the opposite point of view, saying that, no, let us not mix religion and science, let us keep them apart. And this, I think, is a very, very nice lesson for us all. But nonetheless, this philosophical, religious, or philosophical and aesthetic preferences really continued. Late 1950s, there was a Soviet program by Lifshitz, Lifshitz of Landau, Lifshitz volumes that you all know about, and Kalatnikov, saying that Big Bang singularities and black hole singularities are exceptional because they have to do with extreme symmetry. Generally, in real nature, these singularities would not occur. They would not be black holes. There would not be a Big Bang. And then the British school had a famous steady state universe, which was given by Hoyle, but also developed in detail by J.N. Narlikar, Armand Bondi, Tommy Gold, and Denny Sharma till the 70s. And so people resisted the idea of Big Bang. The paradigm shift came because of two things. One is nucleosynthesis was understood. So this, doesn't seem anything to do with cosmology. So why does nucleosynthesis really lead us to believe in Big Bang? Because of the following. You look at the universe around you and you find very, very element. And the point is the heavy element, there's a physics provided mechanism for the production. They could be produced by nuclear reactions in the star that I mentioned some time ago. But if I look at the light elements, their abundance could not be explained using the stars as the oven which cooked them. So lithium, beryllium, and so on, and helium. And to explain their abundance, one had to have a hot phase of the universe much, much early. And that is what these people, these physicists realized, that there must have been a hot phase of the universe. And that is what led to the idea that there was a Big Bang. And then this was really also something that was confirmed completely independently by cosmic microwave background. Namely, there was this hot phase of the universe, and this hot phase, radiation and matter, where the atoms could not form because the temperature was so high that the temperature was higher than the binding energy of the atoms, and therefore you just have these particles floating around, protons, electrons, and photons going around. And when in fact the universe cooled down as it expanded, then there was a cosmic microwave background that was emitted because radiation decoupled with matter. And after that, the light, so to say, was freed up and could actually come out, and we could see this cosmic microwave background, and that is what we see. So here is a cartoon of the universe of this, what I just said. Here is time again, and space is in the horizontal direction. The universe is expanding, as you can see up here. And here is an early epoch, which is only about when the universe was 380,000 years young. Here, matter and radiation decouple, so the photons, instead of just bouncing around, finally could freely go out, and actually they went out, and we see them in our various satellites today. And this spectacular success over the past 2 or 3 decades is because of the powerful interplay between theory and high precision observations. There are 3 satellite missions that really led to this, confirm this picture. The first was called COBE, the second was called the Wilkinson WMAP, or Wilkinson microwave anisotropy, 1989, 2001, and then most recently the Planck satellite, which was launched in 2009, and we have data from here, which really is what gives us a very good idea about the large-scale structure of the universe. And the idea is the following: that when the universe was 380,000 years young, it was extremely homogeneous, and as Lemaitre had envisaged, and therefore we had a perfect black body with temperature about 2.73 degrees Kelvin, as seen today. At that time, it was very hot, but as the universe expands, it cools down, and today the temperature is about this. And this is the picture that you might have seen in
Professor Ashtekar, you've been muted, it seems. Could you kindly unmute? Professor Ashtekar, can you hear me?
Can you hear me now?
Yes, yeah. I don't know, some glitch.
I don't know why this happens. I don't do anything to the screen, but somehow it gets unmuted.
Yeah,
okay.
Sorry.
All right.
Yeah,
Let's go. No, that's just. Did you miss a lot, or
No, not at all. I immediately prompted you.
Yeah, please do that. Thank you so much.
Yeah.
Okay. And here is a black body radiation up here. So this is extremely homogeneous, as you see, except that there are inhomogeneities, which are 1 part in 100,000. So very small amount of inhomogeneities that we see up here. And the beautiful thing is that we know today physics and astrophysics so well that we can actually calculate in detail and show that these inhomogeneities, under the influence of gravity, grow and actually give us a large-scale structure of space and time. And this is kind of the picture of the universe today, which is really there are these networks that are happening up here. So there are galaxy clusters that are forming here and so on. And so this large-scale structure of the universe as it is seen today really came from these tiny inhomogeneities in the beginning. So this really is a huge paradigm shift. It certainly tells you about why the universe is the way it is today, starting from very early stage, very early phase, when the universe was only 380,000 years young. In human terms, from a snapshot of a baby, one day after the birth, providing an accurate profile when the baby becomes 100 years old. So this was 380,000 years. This is now about 14 billion years later. If you take the ratio of the two, then it's the same as 1 day to 100 years. And one sees that, in fact, something. So seeing this baby picture, predicting what the baby is going to be 100 years from now is what we're doing. Imagine how much biology, biophysics, biochemistry, physiology one would have to know in order to make this exact prediction of what the baby would look 100 years from the snapshot at 1 day old. It's fantastic that we can do with our universe today. Looking at the time, do I have an hour? Do I have 15 minutes? Or hello?
I think we started your time 9. Was it 9:40? Okay, so I think so that was I think 8:10 our time. So I think you have about around 20 minutes.
20 minutes, good. Okay, so then go on. So the question is about now we can ask about what is the origin of these homogenities, and I just wanted to say that in this one slide that the current understanding, the best scenario we have is that in fact even before this cosmic wave 380,000 years ago, there was a phase of rapid expansion which is called inflation, and really in the beginning of this inflation what we had were really just vacuum fluctuations of quantum physics. So quantum physics becomes suddenly very important, and these vacuum fluctuations grow in time and they give rise to this cosmic microwave background. So today we have got a deep understanding of the large scale structure of the universe we see today around us, everywhere up here, in terms of not only the cosmic microwave background, but in fact in terms of the what happened much earlier, and what happened much earlier is really vacuum fluctuations. So this is an accounting of the beginning of the large scale structure of the observed universe, starting from nothing. Vacuum is like nothing, but Heisenberg's uncertainty principle tells us that even in vacuum there are fluctuations, and therefore there is again a paradigm shift, namely that the large scale structure really came from quantum mechanics, from just purely vacuum fluctuations. So here it is summarized up here that this, what we see today, what happened up here is really because of vacuum fluctuations of quantum physics, purely vacuum fluctuations, and then they grow into these inhomogeneities, and these inhomogeneities then, due to in classical gravity, go to observe the universe. So the origin up here is really quantum nothingness. So the universe, large scale structure of the universe came from quantum nothingness. This is a very beautiful idea about cosmogony, about how the universe really evolved, and explaining the observations today. And today there is another paradigm shift, namely there is a new meaning of the Big Bang itself. The new meaning is the following. So here is some of you may want to see this. There is a YouTube video, just reasonably short. I don't know, maybe 10 minutes, 15 minutes, something like that. And in the mainstream cosmology, the term Big Bang refers not to an initial singularity, but to a hot phase in the early universe, say at the end of inflation. So the initial singularity, the Big Bang, that is what we sort of came to understand laboriously through the decades, is now on the verge of evaporating, as being replaced by something that is called Big Bounce. And this is the kind of thing that really was predicted by loop quantum cosmology. That was something that Professor Mishra explained when he introduced me. And I could have talked about more work that I have been directly involved in. I chose to talk about this because I think this is of much wider interest. and is not as technical as explaining how the Big Bang is replaced by Big Bang. Big Bang is replaced by Big Bounce. So this is really interesting that these ideas have now become really mainstream cosmology. In this video, there are, I think, about 7 or 8 of us who are interviewed about our views. We are interviewed completely separately. It's a bit surprising. I mean, I saw the video first time. I was a bit surprised that there is such a unanimous agreement about really the Big Bang. So this is a Big Bang, and I come to the last part of the talk, which has to do with the ripples on space-time geometry or gravitational waves. So what we have seen so far is general relativity, black holes, and the cosmology of the Big Bang. In all these cases, there were tremendous paradigm shifts, but it took quite some time for people to appreciate these paradigm shifts. And these paradigm shifts occur, every now and then. It's not just once and for all. For general relativity, coming from Newton, it was more than 200 years. But these paradigm shifts were slightly, but still decades long, but still slightly shorter. And now I'm going to talk about the last paradigm shift, that was ripples, that is gravitational waves, which are really ripples on space-time geometry. We saw that space-time geometry is a physical entity. It can be acted upon. So if you have violent events, it shakes the space-time geometry. If a heavy object will bend it, the heavy object moves, technically its quadrupole moment changes, then in fact these ripples are propagating and they are gravitational waves. So these are ripples on space-time geometry. And in fact, just a year after Einstein discovered general relativity, he worked out what happens in the weak field approximation and found that gravitational waves exist. And he showed that just as a time-changing electric dipole produces electromagnetic waves. So that is what electromagnetic waves are. When the radio station goes on in the morning or something, one has a time-changing electric dipole, and that is what is producing these electromagnetic waves. And the electromagnetic waves can be in X-rays or visible light or infrared or radio waves, etc. Well, in general relativity, in the similar manner, time-changing quadrupole moment of a mass produces gravitational waves. And here is a picture of a gravity wave observatory. This one is from Louisiana. There are 3 functioning now, one in Louisiana, one in the Northwest, in the state of Washington, in the United States, and there is one in Europe near Pisa. And LIGO India will soon join this global network of observatories. And now the Indian observatory will be in Aundh, which is near Pune, in Maharashtra state. And again, just as the electromagnetic waves, many of you engineering students know, have 2 polarizations. So similarly, gravitational wave, H stands for the little perturbation of gravity. So little ripple of gravity. It has a plus polarization, a cross polarization. So if you have a distribution, circular distribution of particles, and if a gravitational wave comes in the perpendicular plane in a direction that is perpendicular to the plane of these particles, then in fact that's shaken, and in quarter cycle they would have this shape. Then again it will come back, and the next quarter cycle it will have this shape, and then again it will come back. There's a plus polarization, and similarly you've got a cross polarization where you got these 2 things. So that is what happens to the test masses in presence of gravitational waves. Now, gravitational waves also have a very curious history, just like what we saw for black holes and for the Big Bang. There is a great confusion until 1960s on whether gravitational waves exist in full nonlinear general relativity, even though Einstein himself had shown in 1916 that gravitational waves do exist in a weak field approximation. So this was all in weak field approximation, or linearized approximation, as one says. That our gravitational waves do exist, but what happens if you include all the nonlinear effects? Sometimes some spurious effects can arise by approximations. And surprisingly, Einstein himself contributed to this conclusion, to this confusion, because he argued on the basis of some work he had done in 1936 that in fact his earlier results were mathematically correct, but were physically incorrect because they were artifacts of the approximation. And so he wrote to Max Born, another kind of founder of quantum mechanics, in 1936, saying that together with a young collaborator who was Nathan Rosen at the time, this is the photograph much later, Nathan Rosen, I arrived at the interesting result that gravitational waves do not exist in full nonlinear general relativity, though they had been assumed to be a certainty in the first approximation. This shows us that nonlinear gravitational wave field equations tell us more, or rather restrict us or limit us more than what we had believed up to now, which is a shocking statement that, in fact, what he had found in 1916 was not physical, and in full general relativity, in fact, gravitational waves do not exist. And there is a curious history up here. The paper, Einstein-Rosen paper, was sent to Physical Review, and it was entitled, "Do Gravitational Waves Exist?" and argued that they do not exist in full nonlinear general relativity, just as what Einstein had said to Born. Interestingly, in that year, Einstein submitted 3 papers to Physical Review, and only this paper was sent to a referee. And the others were the very famous paper, the EPR, Einstein-Rosen Podolsky-Rosen paradox and Einstein-Rosen bridge. They're all correct, and they were published immediately. But surprisingly, the editor had a good enough nose to sort of suspect that there was something incorrect here, or maybe one should look at it more carefully and send it to the to a referee, Robertson. And Robertson was a famous cosmologist who sort of is one of the names that goes under the current cosmological model that we use, namely Friedman, Lemaitre, Robertson, Walker model, and that is Robertson. But Robertson wrote an 8-page report showing that there was an error, not in the mathematics, not in the solution, but in their conclusion, because they had used, for those of you who are more technically oriented, they had confused that what they had shown was a coordinate singularity, not a true singularity. And Einstein and Rosen, however, had very curious reactions. Einstein just withdrew the paper from Physical Review and resubmitted it to the proceedings of the Franklin Institute. And then it was immediately accepted. But in the version that finally appeared, Einstein reversed the conclusion and changed the title, because in the meanwhile, Einstein realized that in fact that conclusion was incorrect. The gravitational waves do exist, and these are now called the Einstein-Rosen gravitational waves in general relativity. But as you can see, that this really caused a lot of confusion in the community, wondering whether gravitational waves do exist in full nonlinear general relativity, or they are just some artifacts of approximations. And there's a great deal of confusion, and the reality of gravitational waves, that gravitational waves is a prediction of full general relativity, really came in 1960s through the work of Herman Bondi and his group, and Roger Penrose and his collaborators. And so actually, when 3 years ago, when the Nobel Prize was given for gravitational waves, many of us thought that Roger would be included, but of course the prize can only be given to 3 people, and they chose people who were directly related to the observations. So on the observational side, this is before, in the early days, in the 1900s, on the observational side, it was established, the existence of gravitational waves was established by careful observations by Russell Hulse and Joe Taylor of a binary pulsar system. These are 2 stars which are going around, they're emitting pulses, so you can understand one of them is emitting pulses, so one can track its trajectory very well. And by the very careful observation, Joe Taylor and his student Russell Hulse showed that these gravitational waves, that in fact the orbit was shrinking slightly, exactly as general relativity would predict, because the system is emitting gravitational waves, therefore it is losing energy, and as a result of loss of energy, it becomes slightly more tightly bound as it comes in, and therefore, and that is what observed, and they received the Nobel Prize in 1993. But this was an indirect measurement of gravitational waves, and the question is whether gravitational waves can be measured directly. So gravitational waves, as I said, are ripples in the space-time geometry, and it turns out that the space-time geometry is extremely rigid. The effective Young's modulus in space-time geometry, you can calculate that, at the 1000 hertz at which the detectors work is about 10 to the 25 times that of the rubber and 10 to the 22 times that of steel. So as you know, I mean, steel is very difficult to bend and to make it vibrate. And the statement is that this is really, space-time is even more difficult to vibrate. The geometry of space-time is even more difficult to vibrate because it is much more rigid than even steel. And therefore, only extremely violent events can make this space-time shake. And hopefully these events don't happen too near to us. Therefore, they happen far away. And as the gravitational waves propagate, just like light propagating to us from very far away, it fades, and the intensity of these gravitational waves fades. And therefore, one needs instruments which are really extremely sensitive. Fortunately, we have them now in terms of LIGO-Virgo detectors. And such events do occur, and the direct discovery of black holes and neutron star collisions has really occurred in the last 5 years. There are many events now, as I showed a little picture a while ago. And the gravitational waves provide detailed images that cannot be obtained from electromagnetic waves, because light coming from these events is scattered by multiple times by the time it reaches Earth. But because gravitational waves interact so weakly with everything, they come to Earth much more directly without these interactions, and we get a good picture of what really happened. And we have a brand new window on the universe, therefore, and that we could not even dream of in Newtonian gravity, because there are no gravitational waves in Newtonian gravity. So here is a direct detection on Earth. Here is the first event that was discovered by a black hole merger in 2015. So this is 2015. 09 is a month, so that is September, and 24. So 24 September 2015, this event was seen in LIGO-Virgo detectors. These detectors are 3,000 kilometers apart from each other, and yet the statement is that, as you can see, this is one detector, this is another detector. You can superpose the two, and you can see that in fact the signals agrees, and therefore, you know, this is not some systematic error or anything like that anywhere, and that this was the detection. And then 2 years later, there was the detection of neutron star merger. And this event, when the neutron stars merge, they really during the merger, they send out a lot of radiation. When the black holes merge, they don't send out anything but gravitational radiation. But here, you also see electromagnetic radiation, many, many wavelengths. And therefore, about 70 electromagnetic observatories all over the world actually followed this over a period of a year afterwards, and the theoretical predictions were all confirmed. And therefore, this resolved the mystery, a long held mystery about one type of gamma ray burst. By the way, now one believes that all the heavy elements such as gold, plutonium, uranium that we sort of like, they are really produced in the universe. They cannot be produced just by the stars, regular stars. The production really sort of tapers down after iron, but these are now, one believes that these are actually produced in the neutron star mergers. In this particular event, it was estimated that something of the order of several Earth masses of gold and several Earth masses of plutonium was actually produced. So this is the end of the main part. So let me just summarize now. I presented a few examples of paradigm shifts in fundamental physics and astronomy. And here is a quote from a famous biologist, and this book is called Consilience, the Unity of Knowledge. And he says, the physicists succeeded magnificently, but in doing so, revealed the limitation of human intuition. Unaided by mathematics and understanding of nature, they discover comes hard. So this is a good lesson for students. You know, you cannot just create theories because you like something. Really, you have to understand mathematics very well, and you have to use it very astutely. And here is a sort of key point. The cost of scientific advance is the humbling recognition that reality is not construed to be easily grasped by human mind. You see, the idea that space-time is curved, you cannot grasp it. And yet it is real, because your GPS system, your telephone would not work without that. But so you have to really have these abstract models, and have to give up the idea that what you think intuitively as being obvious must be true. And the paradigm shifts actually typically exactly establish that what everybody thought for a while to be intuitively true are really shaken. And they really, therefore, illustrate the audacity of the human race to see way beyond what is directly perceived, what the intuition was up to that stage. And so the lessons that we learned are the following. The paradigm shifts are used, this is the same transparency that I began with. The paradigm shifts are used to offer some lessons for young researchers working at the cutting edge of science and also technology. First, what is now considered as commonplace knowledge was not at all so. So you really need courage not to just accept today's paradigm, be suspicious of things that don't fit with your intuition, with your understanding, and so on and so forth. But then you should have the patience to work out the consequences of your new ideas in great detail, great detail, like Chandra did. He worked on the idea of the stars forming black holes for an entire decade, sharpening the ideas further and further. And secondly, precisely because they are so startling at first, the dramatic paradigm shifts take decades. And therefore you need patience to really wait. I mean, the Roger Penrose had this dramatic paradigm shift. It was in 1965, and the Nobel Prize was given just this year. The same thing happened with Chandra. I think the delay between the discovery and the Nobel Prize was of the order of 50 to 55 years in both cases. And finally, you need maturity. Namely, the factors driving or slowing the process are quite varied. You should not think that, well, I found something beautiful, something important, and therefore it will be immediately accepted. No, like everything else, this acceptance is really a social phenomena and is not simple logical steps, and that is made to appear in the retrospect. There can be even non-scientific events like world wars that intervene in order to make these paradigm shifts acceptable. And finally, you need a sense of balance. And this is what I really want to emphasize for younger people. You take the standard paradigms with a grain of salt, and then you pursue with what you believe. But each time you obtain results, you have to re-examine them critically, really critically. Be your worst critic and see if they stand this examination. Only then can you really hope to make these paradigm shifts. Thank you very much for your attention.
Thank you so much, Professor Ashtekar. I think that was an incredible talk, an incredible journey, completely non-technical and yet so detailed and so informative. I think, can we please unmute all the attendees so that we can have a round of applause for Professor Ashtekar? Okay, so I think, Professor Ashtekar, we have a bunch of queries. With your permission, I could probably...
Please go ahead.
Yeah, okay, great. So... Okay, this is okay. So there's a query by Venkatramana Mataparthi, and the query is, what are the latest? Is not directly related to your talk, but your expertise. So, what are the latest improvements in the theory of loop quantum gravity, and can loop quantum gravity and string theory both coexist in our universe?
Okay, so I'll be brief because that was, as you said, was not covered in the talk. So the latest development in loop quantum gravity, in fact, that is what Professor Mitra had asked me to speak about, are in the domain of cosmology. And what has happened is that what was shown in detail, and this was a physical review letter that appeared earlier this year, and some of the news media picked it up under the name of the cosmic tango, the interplay between the very small and the very large. So what we showed was that in the very early universe, there is a very interesting interplay between the ultraviolet and the infrared, the very small and the very large, which leads to certain observable effects, which explain anomalies that the Planck team has discovered, that satellite team that I mentioned has discovered in the cosmic microwave background. By and large, the cosmic microwave background confirms the predictions of standard model of cosmological model very well, but there are some anomalies. And the nice thing about loop quantum gravity is that it leaves these predictions where observations are confirm the standard model untouched, and yet it can explain some of these anomalies. And so that, I think, is the most interesting thing, more interesting development namely that quantum gravity, in loop quantum gravity, the the abstract subject of quantum gravity has left the pristine perch of mathematical physics and is really making contact with observations. At the same time, the mathematical work still goes on. Can string theory and loop quantum gravity coexist? And in my view, I don't see why not. I think that both of these are incomplete in essential ways. Loop quantum gravity, because it comes from general relativity background, emphasizes the geometrical aspects, in particular the idea that the geometry is not only dynamical, but since it is physical in Einstein's theory, in quantum gravity, it should also have constituents, it should have fundamental atoms, and then one should really look at a quantum theory of geometry itself, and then quantum gravity should be developed in conjunction with quantum geometry. Whereas in string theory, at least the focus the earlier on was really in on kind of unification of all interactions, and the two are in some ways complementary. I should say that over the last 2 or 3 years, even some of the people that you heard about in the talks, in the previous talk, who are very, very prominent and deep string theorists, they have come to agree that string theory has not solved, and it doesn't seem to be likely to solve, the basic questions of quantum gravity itself. There is a very nice interview that was given. There's an article that was written by a journalist who was visiting the Institute for Advanced Study, and there are quotes from various people in that article, so you could look at that. You can just say string theory article. I think it appeared in the Wired magazine. And so string theory currently is really a very rich toolbox which can be applied in a variety of contexts. And especially in this light, therefore, I think that there is a lot of potential for tools from string theory to be applicable in loop quantum gravity, which is trying to address the problems of quantum gravity proper.
All right, and there is a follow-up by the same person, and the follow-up is essentially asking about how can a black hole be expressed in terms of loop quantum gravity, and can we relate a gravitational singularity to the graviton?
No. So the second question, the gravitational singularity is not related to graviton. Graviton is an approximate notion that appears, is a very convenient notion that is useful in the weak field approximation. Singularity occurs in the strongest field approximations, in the strongest field limits, and therefore the two are rather different from each other. So the fundamental theory has to sort of, in the weak field limit, produce gravitons, and the strong field limit, because of quantum geometry effects, actually resolve these singularities. So singularities have been resolved, both the Big Bang and the black hole singularities. The work on cosmological sector is much more deeper because there are more symmetries available there. Systems are simpler, equations are simpler. The work in the black hole sector is not as complete, but the singularity resolution part seems to be quite robust, coming from loop quantum gravity. And the reason why it happens is precisely what I said, namely that we have loop quantum gravity is based on a quantum theory of geometry, and as a result, the fabric of space-time that we think about, the continuum that we think about, is a good approximation under everyday circumstances. But in the Planck regime, where the curvature becomes very large, this fabric, so to say, tears, and you have to then describe physics in terms of individual threads. And these individual threads are excitations of geometry for which were equations in loop quantum gravity. And that is why singularities could be addressed.
Okay. So there is a two-part query by Basavraj Kagali, and so it says, how does one explain jets streaming away from a black hole when matter is falling into it from a companion star? And the second is, should one not expect a lot of dark matter at the galactic center, along with the supermassive black hole?
Yes. So there'll be a lot of dark matter. So the answer to the second question is there is a lot of dark matter, but this dark matter is not as concentrated as is needed to account for these orbits of the star. This compact object could not be just a dark matter object by itself. It's some. Okay. The second thing is really, in other words, the dark matter is spread out much more than that. The earlier part of the question was about
streams.
Can you
Sorry, the jets streaming
Okay.
away from the black holes.
That's a very nice question. So the statement there is really that what Roger Penrose discovered was the following: that if you have a rotating black hole, then there is a region outside the black hole, outside the event horizon, in which the energy can be negative. Well, technically, the symmetry vector field, which is generating time translations, called the time-like killing vector field, which is time-like at infinity, becomes space-like in this region. And therefore, and the energy is a scalar product of the forward momentum of the particle with this scaling vector. And if it is space-like, then it can become negative or positive. There's no problem. And so the statement is that there is a region which is called Ergo Region, which is outside the event horizon, where energy can be negative. So what happens is basically as these particles are falling into this Ergo region, and then there is what is called the Penrose process. What Penrose showed was that you could have a consistent picture in which some particles fall into, which carry positive energy. They fall into this Ergo region, but then they might decompose into two particles. And one of them can carry negative energy, and then it will fall into the black hole, and the other can carry positive energy, and it can come out. And the mechanism, and when it comes out, then its energy would be larger than what the energy fell in. And the general models, which really, like for example, due to Roger Blanford, which actually talk about these jets, which explain the jets, use this Penrose process. So the energy is coming in from outside the event horizon, not from inside the black holes themselves. And of course, this process can last only so long as the black hole is rotating. It's really when it's extracting, these jets are extracting the rotational energy and slowing down the black hole. When the black hole loses all its energy and becomes non-rotating, it becomes a short-shell black hole, then this process would stop and one would not see the jets. But during the slowdown of the black hole, these jets will appear.
Okay, there is a query by Shashank, and the query is, what expectations do you have with the new data we will get from the James Webb Telescope to be launched next year, or more projects like the Event Horizon Telescope? Or more, or more projects like the Event Horizon Telescope will be needed. Sorry, that's a full query.
Right. So I think that as far as we'll get more information about the environment around black holes through these telescopes. With the James Webb telescope, we'll also understand this galactic dynamics very well. And one general belief is that the galactic dynamics is largely correlated or almost dictated by the dynamics of the central black holes of these galaxies, the evolution of these central black holes of these galaxies. So one will understand these mechanisms much, much better. In terms of getting a firm prediction or firm confirmation of black holes, I think the best bet is really through gravitational waves, because there, as we saw some plots explicitly, what one does is one does computer simulations of Einstein's equations, and one does computer simulations just because one solves them on computer is what I mean. And the reason why we do that is just because our equations are very complicated, and then one really predicts the form of the gravitational waves that will be emitted, and then one actually sees what the strain in the detector, and one compares it with the prediction of actual Einstein equation, and one sees this precise agreement, which is really fantastic. Such detailed confirmation will not come through any of these astronomical electromagnetic observatories or electromagnetic projects that we are now looking at. We'll get more information about the influence of black holes, but not about kind of the smoking gun evidence for black holes from them.
Okay, so there is a query which says, so it's again by the same person, Sambit Sarkar. It's asking you for commenting on the quantum extension of the Kruskal space-time. Apparently, he quotes year 2018, so maybe he's referring to a work of yours. That's the first query. And the second query by the same person is there, essentially what the query is there an analog of holography, like the the celebrated gauge gravity duality, the so-called ADS-CFT correspondence in loop quantum gravity.
Okay, so the first is about the crustal picture. So that that was a paper in Physical Review Letters, and then a detailed paper in the Physical Review. And the point up there is that we use loop quantum gravity and so-called effective theory from loop quantum gravity. So we did not solve full quantum equations, but rather classical equations which incorporate the leading order H-bar effects, the quantum effects coming from loop quantum gravity. And it was shown that, in fact, the singularity is resolved. As far as that paper is concerned, that analysis is concerned, I think I'm quite reasonably confident that what is happening near the black hole interior, inside the horizon, where the singularity is resolved, that part is completely fine. But we also, for the first time, matched with what is happening inside with what is happening outside. And that part, I think, is not right. I mean, it's not completely, it's essentially it's okay, but it's not completely right. That part will have to be re-examined, modified, understood better, and so on. So the matching, the exterior geometry, I'm much less confident about. The singularity resolution within the limitation of the effective theories, I think, is quite robust. So that the singularity resolution part, I would go by. The second thing is about, is there anything about ADS-CFT? There is and there is not, in the sense that what people recently have done is really looking at just general relativity with the boundaries and looking at what the boundary degrees of freedom are. And then, this idea is that in general relativity or in quantum gravity, the observables will have to be diffeomorphism invariant, and therefore, really, in some sense, the true degrees of freedom would be captured in some suitable sense on the boundary. But there isn't anything that is clean in the sense of a duality. ADS-CFT duality is a conjecture. I mean, there's no proof that one thing is equal to the other. There's a lot of evidence for it, for this conjecture, but there's no proof because we just don't have complete theory on the gravity side, and non-perturbability theory on the gravity side. You can define it to be via this duality, but then there is a definition and not a theorem, not a proof. So we do not have complete proof. Even the string theory literature between ADS, between what is happening on the boundary at ADS and the CFT on the boundary and the ADS which in the bulk up here, asymptotically ADS in the bulk. But nonetheless, whenever one has this conjecture, that conjecture gives precise theories which are supposed to be dual to each other. We do not have anything like that in loop quantum gravity, and I'm skeptical that in 4 dimensions and without supersymmetry, that such a theory would actually exist, which will be, really the two theories being completely equivalent to each other. There'll be deep relations between the boundary theory and what is happening at interior, but I'm not sure that one would have the kind of realization of the kind of ADS-CFT conjecture that is really in string theory.
All right. So there is a query which says, how does one distinguish? So this is by, again, a 2-part query by Ganesh. And it says, the first is, how does one distinguish between the Big Bang singularity and the black hole singularity? And the second, the way it is worded is, how does the big bounce explain early singularity? Not sure that it's probably referring to a slide of yours. So these are the 2 parts of the query.
Okay, so the first is about the Big Bang and the black hole singularity. The Big Bang singularity is what happens near the singularity is very different. So you can take, in both cases, the curvature blows up, but the type of curvature that blows up in the Big Bang and the black hole singularity is quite different from each other. In the Big Bang singularity, if you like, the geometrical, I mean, roughly speaking, the curvature can be divided into 2 parts. One is sort of pure gravity side, which is called the wild curvature, which is like the trace-free part of the Riemann tensor. And the other is called Ritchie curvature, which is the trace part of the Riemann tensor. Einstein's equations directly relate the Ricci part, the trace part of the Einstein's of the Riemann tensor with the matter fields, the stress energy tensor of the matter fields. So in the Big Bang singularity, the wild tensor is 0. So that is to say, if you have, there's no kind of pure gravity singularity there. There are no gravitational wave kind of singularity there. But what we do have is a Ricci tensor is non-zero. Whereas in the black hole type singularity, since black hole solution is near the singularity, at least it is a vacuum solution, and therefore there is no matter there. Therefore, the Ricci tensor is 0, and the wild tensor is non-zero. So the wild tensor blows up in the black hole singularity, and the Ricci tensor blows up in the Big Bang singularity. But for the non-rotating black holes, the singularity is also space-like, and the Big Bang singularity is also space-like, and therefore both can be handled in loop quantum gravity. And the second question I didn't completely get about how can there be a bounce. So
yeah,
the statement.
I'm not sure. Yeah, I'm not
Yeah.
sure what.
So I think what does happen is really that there is no Big Bang, but the Big Bang is replaced by a big bounce. So if you go back in time, the universe would be contracting, right? Because if in the forward in time, the universe is expanding. So the standard Einstein solution, standard solution to Einstein's equation, the Friedmann-Lemaitre-Robertson-Walker solution, would just diverge. If you go back in time, it would just diverge. What happens in loop quantum gravity is that the solution that we have is a good approximation to the Einstein, the classical general relativity solution is a good approximation to what happens in loop quantum gravity until about when the matter density is about 10 to the minus 4 or 10 to the minus 5 times the Planck density, which is 10 to the 94 grams per cubic centimeter. Is enormous, but it's finite. But then after that, there's a huge modification. So until the matter density becomes about 10 to the 10 to the minus 90, say, grams per cubic centimeter, Einstein's equations are good approximation. But once the matter density surpasses that, then quantum geometry effects kick in, and effectively there is a repulsive force, and that causes the Big Bang singularity to be replaced by Big Bounce singularity. So the universe, so to say, going back in time, bounces, right? I mean, it just bounces back up here. And so there is a pre-Big Bang branch to the universe. Now, what is the nature of that pre-Big Bang branch? Well, that depends on the kind of model of the universe that we are using. If you use a current model of the universe that is favored, which is spatially flat, then there is only one bounce, then the universe just keeps expanding on the other side.
Great. So I think we'll have the last query, and the query is by Deepan Bansal, and the query is, are the particles that split in the Ergo region entangled, and does this cause loss in black hole energy?
People have not looked at in that detail. So the statement is that loss in energy. No, the particle which falls in are going to be yeah. So let me start from scratch. Okay. So the process was really done with classical particles, and even though one is talking about decay, the Penrose idea, which is really described by geodesic and some for momentum of the particle. That's how we describe it. So I get a particle which is coming in, and that particle is going to decay into two particles. And when it decays into two particles, one of them falls in the black hole carrying negative energy, and one of them, which is positive energy. By conservation, the total energy should be positive because the energy of the particle outside, which fell in, was positive. And so the energy of the particle which comes out is bigger than the energy of the particle which went in. The negative energy sort of the particle fell into the black hole, and so the energy is actually increased. Perhaps because you're talking about entanglement, you're thinking in terms of entropy and so on. And then the statement is that indeed if in fact one did this and the two particles are entangled with each other, will be typically entangled with each other if in fact they were formed because of a decay of this kind, then indeed what fell into the black hole and what went out would be entangled. And then so there is entanglement entropy between these particles, and therefore really is, at least for a while, it would look like the entropy actually increases the particle which is falling in would be at a pure state, and the particle which is coming out would be entangled with the other particle. So there will be actually, for a while at least, increase in entropy. Now, what really happens in the theory is an open question. In loop quantum gravity, the picture would be that, well, but the black hole singularity is dissolved, and therefore, finally, the particle which fell in would also come out. The total energy is always conserved in this whole process, so there is no problem. That particle would also come out, and then one would actually find that the purity of the state will be restored at the end. But this really depends on what happens at the singularity. Is the singularity resolved, or is the singularity not resolved? If the singularity is not resolved, the negative energy particle will just fall in, and then the total entropy of the universe would actually increase.
Right. Though I said that was the last query, but I found a curious query by Lai Chi Long, and the query is, what will be the next paradigm shift?
That's a very good question. So I think that, I do think that this black hole information loss, quote unquote, question. I think there is no information loss personally, but but this issue is already open. The resolution of that would presumably would lead to some kind of a deep paradigm shift. The other paradigm shifts might come about, but this is a lot. It's not so completely clear from actually gravitational wave observations, because I think there are very interesting ideas nowadays about what one is finding in these gravitational wave observations. Typically, it turns out that if the initial black holes were not spinning, or the spin was completely negligible and they fell in, then the final black hole, it turns out, has a universal spin, which is about 0.7 in the dimensionless unit. The A parameter is about 0.69. So the point is that, and in the observations that LIGO, Virgo have done so far, the spin of the final black hole is all compatible with these predictions of 0.69. And so it looks like the initial spins were actually, the initial black holes were actually not spinning, if this is all correct. These are all error bars and it has to be gel. But if this is the case, then the statement would be that we need a mechanism to say that why the initial black holes, why there is abundance of initial black holes before merger that are not spinning, or would spin very, very small. And there is some ideas that if I look at black hole entropy calculations, and we'll look at the dependence on the angular momentum and mass and so on more carefully, then in fact, these black holes, which are initially not spinning, might be preferred. And so there are speculations about how these black holes could have been formed in a phase transition, which in the early history of the universe, the QCD phase transition. And so I think that if these things are confirmed, there will be really a deep understanding between many, many different branches, with QCD transitions, with black holes, with the classical black holes, as well as the quantum nature of black holes as displayed in the Hawking-Bekenstein formula. So I think that these might be the kind of really paradigm shifts. The other paradigm shift, which has already happened, but it needs to be solidified much more, is that there was no such thing as a Big Bang singularity. I think that is a rather major paradigm shift, and it looks like many people agree with this new view from different viewpoints for different reasons, but they agree with this view. But settling then what really happens would be a big will also cause a paradigm shift in our understanding.
Great. I think with that, I would once again, on behalf of the entire institute, the organizing committee, thank Professor Ashtekar so much for the beautiful talk, and with his patience with all the queries, so many of them. And so once again, thank you so much, Professor Ashtekar. We are very grateful, really appreciate it. Thank you. Thank you so much.
Okay, thank you. Bye-bye now.
Bye.
And as I was mentioning to you before, I was really very impressed by how beautiful Roorkee is, the campus is. And so
we
that's
pray that
the-
we could have the situation would improve, that we could arrange for your physical presence here. And
oh, that would be nice. But I feel happy that you live in such a nice place, and that's very nice. Okay.
Thank you. Thank you.
Bye-bye.
Bye. Please stay safe.
Bye now.
Bye.
Thank you.
Bye. Okay, so with that, I think we come to the conclusion of this interesting and a very, very nice journey that we've been on for the past month and a quarter. And this was the concluding lecture of the Mysteries of the Universe Institute Lecture Series. And I see Professor Gauri Shetty up there, and he is the convener of the Institute Lecture Series, and we are very grateful to the Institute, especially the Institute Lecture Series, for providing us with the necessary support to be able to conduct the series. So I wish all of us a rather early, but a very happy new year. Still not too early, I believe. Thank you so much. Please stay safe. And we would just end on this note that you'll be back with MOU 2 starting next year. And please be on the lookout for the announcements. So I thank once again Professor Ashtekar. I thank Professor Gauri Shetty, the convener of the Institute Lecture Series, and I thank the incredible team of the Physics and Astronomy Club and the Roorkee chapter of the Indian Physics Association for their beautiful support. I wish all of us a good day, good night, and Happy New Year, and see you online, it seems, again next year, early next year. Bye-bye.